I'd like to quickly illustrate the mechanics of the yield to maturity on a bond, which is also called just the yield on a bond, but then focus more on 4 ideas around the interpretation of the yield, because in about a decade of teaching the yield or yield to maturity, we found that the more challenging thing about it is the interpretation of the yield. So to briefly look at the mechanics of the yield to maturity, I would compare it to an exercise I did a few videos ago where we computed what's called the theoretical bond price. So that was a classic exercise where we have 4 inputs and we solve for the bond price. And so using the same numbers I have here, we have face value of 100, so that's face value or future value, the coupon rate, and I'll use my 6% per annum. We needed a maturity on the bond. In this case, I have a 2-year bond. It's a short, 2.0 years. And then when computing the theoretical price of the bond, we also needed the yield. And so the yield is shorthand for yield to maturity. And so we would give the calculator or Excel the yield. Let's say it is whatever it is. I'll let it be X here. And then we would compute the theoretical bond price, or on the calculator use the PV for present value. That's the discounted cash flow or present value, and that's the bond price. So in a shallow sense, when we compute the yield, really we're just providing the present value as an input and solving for the yield. It's just a subtle shift here, right? We take future value of 100, coupon rate of 6%, the number of years is 2, and when solving for the yield, we would provide the present value as the input. In this case, my present value or theoretical bond price is 103.88 cents. I'd put that in as a negative to represent a cash outflow, and negative 103.88. And so that I have those 4 outputs, and I can then solve for the yield, which is 3.962. So in a shallow sense, right, I'm just providing the present value as an input and solving for the yield. Now in Excel, I take it one step further, and I'm more accurate by using the spot rate curve. And the spot rates can also be called zero rates. And so I just made them up. They're in orange. I have an upward sloping spot rate or zero rate curve. You can see here plotted in orange, 2, 3, 3.6, and 4. But I'm also breaking the maturity of 2 years out into semi-annual periods to match the fact that it's a semi-annual coupon rate of 6%. So that's 6% per annum, but payable every 6 months or semi-annually. So that now I would price the bond properly, I should price the bond according to the zero rate curve. So I have the stream of cash flows in their future value, right? Each coupon here is $3 every 6 months. That's 6% multiplied by the face value divided by 2 to reflect the semi-annual. So I have $3 coupons at 6 months, 1 year, 18 months, and then finally at maturity, the final coupon plus the return of principal, so that's 103. As usual, most of the cash is at the end. And then I solve for the present value of each of these future cash flows, or put another way, I just simply discount them, right? So, and you can see this formula here reflects the fact that it's with semi-annual compound frequency, so that my discounted or present value of each of the cash flows, the sum of those is what I've been calling the theoretical bond price. In this case, 103.88. And so the yield to maturity, now as I shift over from mechanics to interpretation, there's 4 ways I'd like to share with you about looking at a perspective on the yield to maturity, right? And the simplest, just maybe the most accurate, which is that the yield to maturity is the single discount rate that we can use that solves for a price that matches our observed market price. So in this case, my yield to maturity is solved for by using Excel's rate function. And I'll just rekey that in because you'll notice I start with a rate function, and then in practice, I first have to decide what my periodicity is, the compound frequency. And you notice I could decide here that I'm going to go with an annual compound frequency. So I could decide, okay, it's 2 years, and my coupon therefore is $6 per year, and I use this price here, although now I'm mixing compound frequencies a little bit, you might have noticed, and my future value or face value is still 100. And then, so I could solve for this, and then I've assumed annual compound frequency, but it doesn't really match my assumptions. So what I really should do when I start here is ask that question. Okay, semi-annual. So that means the number of periods here is really 2 times 2 or 4. And then my coupon payment is my 6%. I like to start with a percent times the face value, and then to be consistent with my semi-annual or 2 periods per year, I divide that by 2. So that's realistically going to be the $3. And then my present value or price is the 103,882. I like to put a negative in front of it because to think about it in terms of a cash outflow as if I'm paying for this bond. And then finally my face value or future value. And so if I stop there, I get the 1.98. And why is that? Well, it's because it's really a 6-month rate, right? I input my assumptions in with a periodicity of 6 months, so I'm getting a 6-month rate. So I need to remember at the end to multiply by 2. It's also called a bond equivalent basis. I multiply by 2 to translate this back into per annum terms. It's a point I've made many times before. In general, almost without exception, inputs and outputs are in per annum terms. So this is a 3.962 yield to maturity, also just called a yield, per annum with semi-annual compound frequency. And so that my first point about interpretation is just illustrated right down here in green, and that this yield is the discount rate that we could use on all of the cash flows to produce here the same discounted or present value price of 103,882. See how the price matches? But the difference over here is, whereas over here I discounted the future cash flows at the 0 or spot rates, over here I'm discounting the same future value cash flows, but at the yield, which is the same for each cash flow, right? Over here, each discount factor effectively is different because the spot rates are different. But over here, my discount rate is the same, and that's the definition of the yield to maturity. So that if we go back to my plot over here, where in orange I have the 0 rates, if I want to plot the yield to maturity, because it's the single discount rate that produces a discounted present value that matches our observed price, the only way to really plot it is with a horizontal line. So my second point that I would just share about it is also, in terms of interpretation, is also somewhat mathematical. And that is that, and it's related to this idea that it's a single rate. In fact, it's the same idea. The yield to maturity is an internal rate of return, which in some contexts is more familiar to some people. And so, and I get the same notion there, the same answer there. So for example, if I just bring the price up here to the top of this stream of cash flows, then I can use the IRR function on this array, right? Treating this just as a stream of cash flows where I start with the outflow, the price, and then I remember to translate it back to annual. I get the same yield to maturity. So verifying that the yield to maturity is an internal rate of return. Okay, however, it's on the traded price. So this is where the yield is more realistic than the theoretical bond price, which is to say that the idea with the yield to maturity is it takes the price as an input, and we don't expect the price to trade at the theoretical bond price. The theoretical bond price is just based on these fundamental factors, but the actual traded or observed bond price is subject to also of what we might call technical factors, or sometimes we call market factors, including my favorites: supply, demand, and liquidity. So, for example, let's just say their technical factors caused this. I'm going to be very dramatic, caused the bond price to just plummet down to $97. Well, the yield to maturity still works and is really designed for that, right? The yield to maturity is now saying that it is 7.6% based on this price input. So we could look at another way. If we purchase this bond at $97, we're getting 6% on the coupons, but notice it's at a discount to the face value. That price will be pulled to par, so we're going to get some capital appreciation. And so the amount that's above the 6% reflects that capital appreciation. So the yield to maturity is really a reflection of whatever the bond price is. It incorporates the information of the traded bond price. In the same way that if I went back to the 103 here, and let's just say the bond price happened to trade pretty close to that, my yield to maturity, again, is just 3.9%, and that reflects the 6% coupon that we're getting, but the bond price is trading at a premium, so as it approaches maturity, it's going to pull the par down to 100, and we're going to experience a capital loss or depreciation on the price. So here, notice that difference is negative. We're getting that 6% coupon, but the yield is reduced to reflect we're going to lose money as the 104 gets pulled down to 100. Okay, and then just final 2 points. And I'll switch this back. The yield to maturity is also a complex weighted average of the spot prices. And the reason I point that out is just for a very practical reason, and that is that if we're short on time on an exam, for example, in practice, this yield to maturity of 3.962 is going to be a weighted average of these spot rates, and you'll notice as usual, most of the cash is at the end, and my 3.9 is pretty close to the 4%. So here, if I'm using the theoretical bond price, my yield to maturity is going to have to be between 2 and 4, and it's going to be closer to the 4%. Again, yield to maturity is also a complex weighted average of the spot rates, a single number that impounds all the information of the spot rates. And my final interpretation point is that, let's say we have this setup, the yield to maturity is 3.962, is represented by a single line. And one of the questions is, does that mean this is the realized return on this bond if we bought this bond at this price? The answer is no, it does not. It's the internal rate of return, so that the yield to maturity here of, let's say, 3.962% will only be the realized return if we hold this bond to maturity and if we reinvest these coupon cash flows at the same yield to maturity, because the bond has both interest rate risk, also called duration risk, and reinvestment risk. So that fourth point is that yield to maturity will not be the realized return unless we hold to maturity and we reinvest the coupons at the same yield to maturity. So I hope that's helpful.